Hello and welcome to Honors Function. This is the last lecture of this unit, a unit on sequences and series. This is also the second lecture on series. In the previous video, we looked at the concept of infinite sum, and more precisely, we looked at three infinite sum. Two of them did not have a finite sum, two of them diverged, one of them had a finite sum, it converged. In this lecture, we're going to make this concept of convergence or divergence more precise. We're going to be looking at an infinite sum more formally. Let's begin. So before you add an infinite number of terms together, you need to have an infinite number of terms. Therefore, we need a sequence. Now, with this sequence, we define another important sequence called the sequence of partial sum. It's a sequence that is defined with a given sequence. Starts at 1 and ends at infinity. What is that sequence? How do we define it? Likewise, S1 is equal to A1, S2 is equal to A1 plus A2, S3 is equal to A1 plus A2 plus A3. Well, you get the gist of it. Sn will be sum from I equals 1 to n of ai, and on and on and on. Okay, so we define this sequence. All right, so given a sequence of term, we define the sequence of partial sum. Now, suppose that the sequence of partial sum has a limit. So we're going to assume that the limit of Sn as n approaches infinity exists and is equal to L, is finite, right? Now, what does that mean, the limit of a sequence? Well, hey, we know what that means. This was lecture number 63, I believe, when we looked at limit of sequences. This is a sequence. I'm allowed to look at the limit of the sequence, right? So suppose it has a limit and that this limit is L, then what is Sn as n approaches infinity, right? As n approaches infinity, if this tends to infinity, then what are you adding? You're adding an infinite number of terms, right? So this right here is actually sum from I equals 1 to infinity of ai. And we will say that this sum is equal to L. This is a definition of a convergent series. We will say that this series is convergent. It has a finite sum that is L, if and only if this sequence, the limit of the partial sum, is actually equal to L. This is actually the definition of a convergent series. Okay? For the series to have a finite sum, we need a sequence of partial sums to have a limit, right? And this is why sometimes I will call that the limit. Instead of calling it the sum, I will call it the limit of the series. Okay, it's a limit of the partial sum. Let's see how it works concretely. So in the first three examples, I'm giving you three sequences and I'm asking you to decide if the series that you will associate with each sequence, if this series right here, is convergent or not. And if it is convergent, I'm asking you to find that limit, that sum. Okay? So let's look at the first one. Well, hey, you recognize that this is the explicit form for an arithmetic sequence. The first term is -2 and d is 0.5 right here, right? And so that's just an. So let me write an in a different way. So an is -2 plus 0.5 times n minus 0.5, right? I just distributed my 0.5, and so it is equal to -2.5 plus 0.5 times n. Now, I'm asking you to tell me if the sum, the infinite sum of all these an, actually let me take n this time, of all these an is finite, if it has a limit or not. Now, in class, we've already answered the question after the first video, and we know it is pointless to look at an infinite sum of terms coming from an arithmetic sequence because you're adding the same constant from one term to another. Therefore, how could this have a limit? It's just going to grow larger and larger, or smaller and smaller if what you're adding is negative. But I don't want to think about it this way. I want to look at it with our formula, with our definition. So with this sequence, we're looking at the sequence of partial sum right here, and we are wondering if the limit of Sn exists as n approaches infinity. So what is Sn? Hey, we know the partial sum of an arithmetic sequence. It's n times a1. So what is a1 right here? a1 is, for n equals 1, it is negative 2. So negative 2 plus an, well, we have an right here, negative 2.5 plus 0.5 n, divided by 2. That's Sn. And so if you look at that, you would find, so negative 2.5 and negative 2 is negative 4.5. Negative 4.5 times n is negative 4.5 n. And right here, I'm going to put 0.5 n times n is 0.5 n squared over 2. Now we're looking at the limit of Sn as n approaches infinity. Now guys, this is a question we've answered very early on this year. This is just a limit, the n behavior of a function, right? 0.5 n squared minus 4.5 n over 2. And actually it's the n behavior of a function that we know very well. It's the n behavior of a quadratic function. And if you look at the n behavior concave up of a quadratic function, this is going to be equal to infinity. Therefore, this series does not converge, it diverges. It's actually equal to infinity this time. It diverges. We knew that again from today's, but it's good to look at it through the lens of the definition. There are two more. I want you to look at these two and answer the question, do the associated series converge or not? And if it converges, find the limit. Let me move on. So as I've mentioned in the previous video, we are only going to be looking at one type of series here, the series coming from a geometric sequence, when you add terms from a geometric sequence. So why a geometric sequence? Well, because it is the first type of series we'll look at when we study series. It's the easiest to study, and it's also a very important one. It does play a central role in the studies of series. Okay, so it's the first one, and at the same time it plays a central role. So here it's going to be a 1 plus, what's the second term? Well, it's the first term times the ratio. What's the third term? First term times ratio squared, and on and on and on. And it goes on like that. A1 times r to the n minus 1, that's the nth term, plus etc, etc, etc. Okay, so this is a very interesting series. Let's try to understand if and when it has a finite sum. So for that, we look at the sequence of partial sum Sn from n equals 1 to infinity. Now, this is also why we are studying geometric series, because we know how to express Sn, right? We know how to express Sn. Sn is a1 times 1 minus r to the n over 1 minus r, right? So I can rewrite that as a1 over 1 minus r times 1 minus r to the n. And because Sn is expressed in such a way, we know everything there is to know about a geometric series. So again, we want to study the limit of the partial sum as n approaches infinity, if you add more and more terms together, right? So this limit is equal to what? It is equal to the limit of a1 over 1 minus r times 1 minus r to the n as n approaches infinity, right? All right. Where is your index for the limit right here? Where's the index for the limit? Well, it's not here, it's not here, it's here. Okay, so if this is a constant, I can just move my limit inside right here, and I will write this is the same as a1 over 1 minus r times the limit of 1 minus r to the n, right here. Now again, this is not a function of n, right? This is not a function of n, so my limit can move further inside, and I have a1 over 1 minus r times 1 minus the limit of r to the n as n approaches infinity. And this, guys, goes back to a result we covered in lecture 63. We know this limit, okay? The only case that is interesting to us is when this limit is 0. We know it is a 0 if r is between 1 and -1. I don't care about the other case when r is 1, okay? What's going on here? Let's look at it if you want. When r is 1, what's going on? Because that's part of my result in lecture 63. Please check out the result from lecture 63. What's going on if r is 1? Well, let's look at the series again. If r is 1, what are you adding together? You're adding a1 plus a1 plus, I multiply by 1 all the time, right? To go to the next term, a1 plus a1 plus a1 plus, well, that is not going to be converging anywhere. This is going to be equal to plus or minus infinity, depending if a1 is positive or negative, right? So this is not an interesting case for us to look at. Let's continue then. If r is between -1 and 1, this term right here goes to 0. Therefore, 1 minus 0, therefore, this parenthesis is going to go to 1, and a1 over 1 minus r times 1 is just going to be a1 over 1 minus r. And this is a result that you ought to remember. If r is between 1 and -1, the sum from n equals 1 to infinity of a1 times r to the n minus 1, okay, I need minus 1 because don't forget my first term has to be a1 right here, or my formula is not gonna work, right? a1 is equal to a1, okay, my second term is a1 times r, okay? You got to make sure you're looking at the first term always. This sum, this infinite sum, is equal to the first term divided by 1 minus r, okay? And again, I repeat what I said. Please make sure you understand that this is your first term, whatever the first term may be, okay? So, very important. This is a hugely important criteria when it comes to geometric series. We need the ratio to be between -1 and 1. Let's go over some examples now. All right, example number 1. So I know this is an example we've done yesterday in class. I just want to show you how it works with the formula. So when I look at this series, I always write the first few terms, so I know what the first term is. So right here you start at n equals 0, right? So at n equals 0, what do you have? You have 1 plus 1/2 for n equals 1, plus 1/4 for n equals 2, plus 1/8 for n equals 3. I mean, you can stop right here, okay? It doesn't make sense to go further here. I know what's going on. Now, what's going on here in terms of the series? Well, are you dealing with a geometric series? Yes. How do you know? You multiply by 1/2 all the time to go from one term to the next. So it is a geometric series, and 1/2 happens to be between 1 and -1. So that means this series is convergent. I know it is a convergent series now. That was my criteria. And because it's a convergent series, I'm going to tell you the sum. It's a geometric convergent series. Therefore, the sum is the first term, so 1, divided by 1 minus the ratio, 1 minus 1/2. So it's the first term, 1 over 1/2. 1 over 1/2 is 2, which is what we had yesterday, right? Here's the first one. Second example. So second example is very similar to the first one, and we could easily answer the second example without going over the formula, just by looking at the first one and seeing what I'm missing. Look, let's write the first few terms here. You start at n equals 1, right? So this time you're going to start at 1/2 plus 1/4 plus 1/8 plus etc, etc, etc. So if on the previous one I started at 1, right? If by adding 1 I find the sum of 2, then when I start at 1/2 I should have a sum of 1, right? But again, let's go with the formula. So for the same reason, this is a geometric series and the ratio is 1/2, therefore it converges. Now let's look at the limit. The limit is going to be the first term, 1/2 over 1 minus 1/2. And so it is 1/2 over 1/2, which is 1. Okay, again, I could have done that easily without looking at the first term, just looking at the first limit we found, but it's pretty easy to look at the formula too. Okay? All right. I'm gonna let you deal with number 6. Let me move on. Actually, please do number 6 and number 7. I'm gonna do number 8. So I could write here the first few terms. It's not too difficult. But before I do that, I really wanna change the way this series look like, the general term of my series look like. I don't like the way it looks, okay? I want to see one n, not too many. And sometimes it's not always possible to do that. But here I can. Let me show you how. So -5 to the 2n is -5 squared to the n, right? That's what 2n is. And at the bottom I have 4 to the n times 4 to the -1. All right. 4 to the -1, that goes on top, times. So here's a power of n, here's a power of n. I'm just going to take it out. What's at the numerator? -5, I guess I should have put a parenthesis here. -5 squared, 25 over 4. Okay, so 25 over 4 to the n. This is a term of a geometric sequence. What's the ratio? The ratio is 25 over 4. Now 25 over 4 is way above 1. Therefore, this series does not converge. The sum right here does not exist, maybe. I'm not sure we say does not exist. It's actually equal to infinity. So maybe it does not exist is fine. It diverges. Okay, here. I'd rather see right here, diverges. This infinite sum diverges. Please do number 9, and I'm going to go over number 10. So number 10. I'm asking you first to find this infinite sum. So let's start with that. So what's going on here? Again, I'm going to do what I just did. 3 to the power of n over 5 to the n plus 1. I'm going to write this as 3 to the n over 5 to the n times 5. And this is just 1/5 times 3 over 5 to the n. Okay? So this is the term of a geometric series. The ratio is 3/5. It is between 1 and -1. Therefore, this sum converges. This sum converges. Okay? Let's write the limit. So for that, again, I'd like to know what my first term is. So sum from n equals 0 to infinity of this, right? Of 1/5 times 3/5 to the n equals, so what's the first term here? The first term is 1/5 plus, what's the second term? N equals 1, so it's 325, and then it goes on and on and on, right? Plus 9 over 75, plus etc, etc, etc. Okay? Alright, so the first term is 1/5, so the whole sum is 1/5 over 1 minus the ratio, 3/5. Hey, don't make this problem too difficult. Multiply both sides by 5 right here. Okay, we've done that before. And therefore the sum is, what do you have at the top? You have 1 over, and at the bottom what you have? 5. 5 minus 3. 5 minus 3 is 2. So the sum is 1/2. Alright, look at the second question and find n so that this is a partial sum. The partial sum is within 0.0001 of its sum of its limit, and that means infinite sum. The partial sum is within infinite sum, okay? 0.0001 of its sum. Let's understand what that means. Look what you are doing, guys. I'm gonna try to show you on a line what's going on. So suppose this is 0, 1, 0, 1. Here I have the sum of my sequence right here, the sum of my series, 1/2. What am I adding together? These terms. So suppose 1/5 is like right here. Here's 1/5. It would be maybe smaller than that, okay? But I need to make space. That's the first one, that's 1/5. What's the second one? 325. Well, suppose it is right here. Suppose this is 325. Again, it would be much smaller than that, okay? Then the next one, 9/75. So this is even a bit smaller, right? 9/75. So suppose this is 9/75 right here. That's the next one. And you keep on adding these terms right here. The next one will be smaller, smaller, smaller. And when you add them all together, all of them, you find 1/2. This is what I want to do in this question. I want to figure out a finite number of them that I'm going to add right here. So I want a finite number of them added together. So if it's finite, we call that Sn. So that the distance between Sn and 1/2, this distance is within 10 to the negative 4. I want to be close to the whole sum, and I want to be 10 to the negative 4 away from the infinite sum. So basically, the question, translate in English and math, I guess, would be, you want the distance between 1/2 and Sn. Okay, 1/2 is above Sn, right? All the Sns are smaller, and they are the terms that you're adding are all positive, so it's below 1/2. You want this distance to be smaller than 10 to the negative 4, so you need to solve for n. You need to solve this inequality for n. If you didn't know if Sn is above or below, then you would have to express it like this. Absolute value, the distance between 1/2 and Sn, the distance between 1/2 and Sn is smaller than 10 to the negative 4. But again, because we know the sign and we know Sn is smaller, we don't need the absolute value. All right, let's solve this and we're done. So how do we solve this? Oops, right here it's negative 4, sorry. All right, let's solve it. So we have, I'm going to move Sn here and I'm going to move that there. So we have Sn above, right? If you move it here, it's going to be above, right? Above what? Above 1/2 minus 10 to the negative 4. Now, what was Sn? Sn is the first term, so it is 1/5 times 1 minus the ratio, 3/5, to the power of n over 1 minus 3/5. That's Sn right here, right? And we want that to be above 1/2 minus 10 to the negative 4. All right, so this is 2/5, and 1/5 divided by 2/5, that's 1/5 times 5/2, so it is 1/2. Right, so this ratio right here is 1/2. Let me go below. So we have 1/2 times 1 minus 3/5 to the n is greater than 1/2 minus 10 to the negative 4. Let's multiply by 2. 1 minus 3/5 to the n is greater than 1 minus 2 times 10 to the negative 4. Let's move this here and the whole thing there, right? Okay, so now what do we have? We have 3/5 to the n. Now, smaller, right? Because it's on this side. So smaller than, what do you have here? 1 minus, so minus what? 1 minus 1 minus 2 times 10 to the negative 2. So 1 minus 1, 0. This is just 2 times 10 to the negative 2. Sorry, all these negative 2, you got to be careful. That's a careless mistake. It's negative 4 right here. Okay, sorry about that. And so what do we have? Let's take ln, right? This is my inequality. Let's take ln. N times ln of 3/5 smaller than ln of 2 times 10 to the negative 4. All right, that's pretty simple now. Be careful not to make a mistake. N is above ln of 2 times 10 to the negative 4 over ln of 3/5. Okay, so whatever that number is, here I'll just say that n actually has to be equal to, so I'm going to take the floor of this, ln of 2 times 10 to the negative 4 over ln of 3/5, and I'm just going to add 1 to it, above or equal to that. Okay. If you take your calculator, you're going to find 17. Please check with a calculator that s of 16, and I showed you how to add some right here. Okay. S of 16 is more than 10 to the negative 4 away from negative 1/2, right? So if you do 1/2 minus x of 16, that should be above 10 to the negative 4. But if you do 1/2 minus s of 17, that should be within 10 to the negative 4. Check it out with the calculator. I hope I haven't made a mistake, but this is already too long and I don't want to do it myself. Okay? Thank you for watching.